Let's talk about Newman projections. If I've got a compound that has got only 4 carbons, let's say I've got this one, a carbon here, it has got an hydrogen here, and a hydrogen, another hydrogen. This is bonded to another carbon, which also has an hydrogen on top, and then an hydrogen there, and hydrogen here. So when I'm talking about Newman projection, this is simply a three-dimensional shape where I'm looking through this carbon. So my eye is from this direction, and then I want to see straight through this molecule. So what is going to happen in this case is that this carbon is going to overlap this carbon. I'll not be able to see this carbon which is at the back, because this hydrogen and this hydrogen, they are all on top. I'm not going to be able to see this hydrogen. Same, this hydrogen is also going to overlap with this hydrogen, so I'll not see the one at the back. Same with these two which are down. So in this case, what you do is I'm just going to write this carbon which is here, and I'm going to put a dash there. I'm going to show the hydrogen that is coming on top, which is this one. So I'm going to put it on top here, and then also the two hydrogens which are on the sides, I'm going to write them like that. So I've written this portion which is in front, and for those which are in the back, I'm going to write another circle like this. So this bigger circle is representing the carbon that is in the back. Okay, now again for this one, we can see we have got an hydrogen on top, so it should be very close to this other one is on top. And then also the other hydrogen is here, the other hydrogen is here. They are more overlapping each other. Now just to show that there are also other elements this side, that's why I've shown like this. Otherwise they are overlapping, we might not even be able to see them the other side. So a configuration that we're able to see like this one, this is called an eclipsed configuration, because it's an eclipse. Like you can't see this, they've been covered, just like when the sun is covered by the moon or the other way around. Now there is also another form. Let's say I've got still a carbon here, still with the same hydrogens in this way. Now I've got another carbon here, but instead this other hydrogen is down, and then the other hydrogens on top are like this. So if I want to write this one first, I'm going to show this carbon which is at this point with a dot. We have got an hydrogen on top, another hydrogen this side, then another hydrogen this side. Let me just make it a bit of straight. Okay, so this is how it's going to be. Now again, what am I going to do? To show the carbon which is behind, I'm going to put like this. Now for this one, we can see that the hydrogen is down, so I'm going to put the hydrogen down. This line shouldn't extend to the other carbon because it's bonded to the carbon that is behind. And then another hydrogen is going to be here, another hydrogen is going to be here. These are the hydrogen which are able to see in the back. So this kind of configuration, we call it staggered configuration, because the hydrogens are not overlapping. So this is called staggered. Now the staggered configuration has got much more energy in comparison to the, sorry, by me saying much more energy, I don't mean it as high in energy. That is just a misuse of a word. This one is more stable. The staggered configuration is more stable than the eclipsed. The eclipsed, because you can think of repulsions that is coming from the atoms. You have got one hydrogen on top, another hydrogen. So these are more like near each other, thinking about that repulsion. But if you compare this, there is more space here for that repulsion. So that is why the staggered configuration is much more higher in, much more stable in comparison to the eclipse. So if I want to show how energy is going to be in this kind of configuration, we are going to have energy on the y-axis, and then we are going to have the angles that is between these carbon atoms and the hydrogens, I mean, on the y. So what we are going to be able to see is that we're going to start going like that with higher energy. The energy is going to drop, the energy increases, the energy drops, the energy increases, just like that. Now, can you determine which one is going to be the most? Where do you what do you think is this going to be? Is it a staggered configuration or the eclipsed? Now, if something has got higher energy, it means this is not stable. Think of it, you are running to the market to buy something. You are not stable in such a case because you are using more energy. When you start working, you are using less energy and so you are stable. So I expect this to be the most stable, and this should be the staggered configuration. So this should be staggered, and then the ones which are on top should be eclipsed because there is no much stability because the bonds are much more closer to each other. So for this one, this is the one which you are seeing. Okay, let me put it like that. Because this one is on top, it has got less energy. This is the eclipse. It has got hydrogens like that. They are very much more closer to each other. And then the one with lower energy, which is down here, this is the one you're able to see. Hydrogen there, hydrogen here, and then the other carbon. And there is much space. Hydrogen here, and hydrogen here. So starting this one, we can see there is basically no angle between these two hydrogens. So this is 0 degrees. We are moving in 60s. So at this point we can see the angle between here is 60 degrees. So this is going to be 60 degrees. If I add another 60, I'm going to reach at 120, and still there's not going to be any stability at 120 degrees. If I add another 60 at this configuration, this is going to be 180. They are very much far away from each other. I add another one, it will give me a higher energy which is at 240, continuing to go like that. So I'm able to determine the angles at which these configurations are going to be much more stable than the other one. Now for this one I've talked about is when you only have two carbons. Okay, you only have two carbons in this one. You saw one carbon and then another carbon at that point. Now what if the molecule you are talking about doesn't only have one carbon? By the way, just what I'm talking about, this one, you have got one hydrogen on top, hydrogens also in this other side. So what is going to happen is that there is going to be some energy that is because of the repulsion from these atoms. So we call that as the torsional strain energy. So when I'm talking about an eclipse configuration, the carbon to hydrogen bonds, the repulsion between the electrons in the carbon hydrogen. So we have got a carbon here and then hydrogen here. Also have a carbon here and hydrogen here. That energy we call it the torsional energy in a case of the eclipse configuration. Now this torsional energy, what happens that is going to be increasing as the angle gets to reduce. The energy is going to be reducing and reducing as the angle gets to increase. That's why you saw that the eclipse has got much more higher energy in comparison to the staggered configuration. Okay, what if we have got a compound that has got more than one carbon? Let's say this compound has got the formula CH3, CH2, CH2, and then CH3. How are you able to write now the configuration for this one, the Newman projection configuration for this one? In a case like this one, you will not be able to take all the carbons at the same time to say, okay, this carbon, the first one I'm going to see it like this, the other one I'm going to see it like that, the other one. You are going to take two carbons at a time when you're talking about this configuration. So in such a case, then what are we going to do? So I might just take two carbons. Let's say I take carbon number 2 and carbon number 3, and then I start viewing using only these two carbons. What does that mean? So if I am to write this properly, starting from carbon number 2, I'm going to have carbon number 2. It has got 3 hydrogens. I mean 2 hydrogens. Let me say one hydrogen is this side, another hydrogen is this side. Then I'm going to take this group to be on top. And then I'm going to write again a bond, and then I'm going to come to this other carbon. Let me say this group is on top, or it can be down. Let me put it down, CH3. Remember, this carbon has got still 2 more hydrogens, so one hydrogen is going to be this side, one hydrogen is going to be this side. So this is how you get to write this. In case of butane, you are going to only take these 2 carbons which are on the middle, and then the others you take them as groups like that. So in such a case as this one which I've written, we are going to have first this carbon. We have got a methyl group on top. We have got a hydrogen this side, another hydrogen this side. And then the others are going to be behind. Now for the carbon which is behind, we have got hydrogen here, we have got hydrogen here, and then we are going to have the C83 down. I can have another form for the one which is in front. I'm going to maintain it the way it is, CH3, and then we have got a hydrogen at this point. We also have a hydrogen at this point, and then I have got like this. Now in this case, let me put this bond. I can now write the staggered the eclipse configuration. So for the eclipse, this bond, I'll just rotate this one for a small angle. So what is going to happen in such a case? This bond can come here, the CH3, and then the hydrogen can come here, the other hydrogen is able to come there. And then I can write still another configuration. I'll still maintain this one which is on top, and then I've got hydrogen at this point, also have another hydrogen at this point. Now in this case, if I write this, let me say this group was here. I can put it here, the CH3, and then the hydrogen is here, and then the other hydrogen is also there. Let me write the last one now. I still have the carbon which is in front with the CH3 here, and then there is a hydrogen here, there's another hydrogen there. Now the eclipse configuration again, this carbon, the methyl group, let me take it closer to the other methyl group, is here, meaning that the other hydrogen is going to be somewhere here, and then the other hydrogen is going to be somewhere here. So these are some configurations that we're able to see. Now these configurations are going to have different energies, different from the ethane that we saw, which had only 2 carbons. So if you look at this one, this group and this group, these have got more electrons. Now because they have got a maximum distance from each other, I expect this to be the most stable compound. Now if you look at this one, the methyl group is closer to the hydrogen. There is going to be a repulsion, steric hindrance. Electrons are going to be repelling each other. So this is going to be less in energy. This one is much stable. Now if I look at this one, well, the CH3 and the CH3, they are going to be repelling each other, even if there is an angle here, because these have got electrons. So this one is going to be less stable. Now this one, you can see the CH3 and the CH3, they are so much more close to each other. So this is going to be the least stable in this one. Why? Because there is an increased repulsion, or the torsional strain is very, very, very much high. So then how are we going to be able to see the energy diagram for such a representation? So I'm going to give these numbers. Let me say this is 1, this is 2, 3, and then 4. Let me have energy on the y-axis, and then I've got the angles on the x. So what we are going to be able to see for this one is we're going to just start properly with higher energy, going to drop like that, come somewhere. It will not, of course, come too much low. Let me take it like that. We are going to have a point where we have got the most stable, because the energy, you can see it goes much more down. Then it comes at this point, and then it goes like that. So the angle at this point, which we're able to see, this is going to be 0 degrees. We are still adding 60s. This is going to be 60 degrees. And then at this point, this is going to be 120 degrees. This is going to be 180 degrees. And then we are going to have also this one maximum, that is going to be 240. We have got this one, which is going to be 300. And then we have got this one at the end, which is 360. So can you guess which structure is going to have which energy on these two, on these four structures which we've written here? Well, the least stable at 0 degrees and at 360 degrees is the one where the methyl groups are together. The methyl groups are together, meaning structure number 4 is going to be here and also here. These have got the least energy. And then we have got these two which have got also, they are less stable, their energies is high. Then which ones are these going to be? This is the one which you are able to see. You can see there should be a hydrogen, not this one. Have I drawn that structure? Okay, so there should be another structure such that okay, I think this one, we have got a group here, we have got also another group here. You can see the methyls have got a maximum angle from each other. They've got 60 degrees away from each other. So this is going to be stable. So this is the group that we're able to see at this point. So this is going to be, this is group 3, this is going to be at this point. And this one, the stability is going to be much more similar to this one. You can see the hydrogen and the methyl, they are just, of course they are close to each other, but the repulsion is not going to be that much high. Why? Because this is just a hydrogen that's got few electrons in comparison to the methyl. Now think of this, both are methyls. Even if the angle is a bit of high, the repulsion will still be high because they've got a lot of electrons, other than this one. This one has got fewer electrons in comparison to this. So basically these two, the energy is not that much different from each other. So then this is going to be the structure 2. Now what of down? Which structures are we able to see at the bottoms? So we have got this one, this one. Let me see if I've not even mistaken what I've written here. Okay, let me first talk about this one, which has got a bit of more energy, and also this one which is at this point. Yeah, so this one was a mistake I mentioned. So these two, because they've got some bit of, they are a bit of away from each other, the repulsion is going to be not that much high because they've got at least a distance away from each other. So this one is going to be a bit of more stable in comparison to this one. So the 3, we are going to be able to see it down here. Okay, even at this point it will still be 3. Now for the top, which is at this point, this is the one where these are very much close to each other, because the repulsion is going to be at least that high. At least this one, they've got a bit of a distance, so that distance is going to reduce the steric hindrance. The hindrance is not going to be that high. So structure 3, structure 2 I mean, is the one which we're able to see on top here. And then the most stable is when these two groups are away from each other, making 180 degrees. So this is structure 1 at this point. So this is how you get to determine the energy of all these compounds. So that is going to be it for this one.